Hello guys, welcome back to my YouTube channel. I'm Afranta, second year MBBS student studying at Government Thuthukudi Medical College. So today I'll be explaining you the two most important 15 marks of biochemistry, that is heme synthesis and porphyria. So there are high chances that they might ask you these questions in your university exams. So let's get started into the video. Okay, let me tell you what is porphyria. It is a rare disease which occurs due to the defect in the heme metabolism. It can also be presented either with neuropsychiatric manifestation and also with the photosensitivity. Okay, I'll just tell you the heme metabolism later. Now look on with the introduction of the porphyria. As I told you, porphyria it can be presented either with neuropsychiatric manifestation and also with photosensitivity. Whenever there is neuropsychiatric manifestation, there is accumulation of ALA and the PPG. And there is no presence of porphyrins in the urine. So automatically there is no Soret band present. So what do you mean by Soret band? Okay. So when you analyze a urine in a spectroscope and if you observe a red color band in it, it is due to the presence of the porphyrins in the urine. So it means that there is presence of a Soret band in it. But in if the cause is due to neuropsychiatric manifestation, there is no Soret band present because there is no porphyrins present in the urine. But if there is a photosensitivity cause, there will be detection of the porphyrins in the urine, so automatically there is presence of Soret band. Now coming on with the structure of the porphyrin and the porphyrinogen. There are 4 pyrrole rings. But in porphyrin, along with the 4 pyrrole rings, they are connected with the help of a conjugated double bonds. But in porphyrinogen, 4 pyrrole rings, they are connected with the help of the single bonds. So in porphyrin, because of the presence of these conjugated double bonds, they can absorb the light at 400 nanometer and they can emit the light at 600 nanometer. So just remember that whenever a light of 400 nanometer is observed, due to the presence of the porphyrins in the body, 600 nanometer light it is emitted. As the 600 nanometer light, it is close to that of the wavelength of the red color light. When it is emitting, it will produce red in color. So yeah, this is the reason for the red color fluorescence that is observed in the presence of the porphyria. Yeah. Now coming on with the erythrodontia, skin will look red in color due to the accumulation of the porphyrins. Well, so as I already told you the neuropsychiatric manifestation, there is accumulation of the ALA and PPG and also they are toxic to the neurons. So there are 2 defects over here. The first one will be ALA dehydratase deficient porphyria and the other one it is acute intermittent porphyria. I'll tell you the heme synthesis steps later, just look on with these steps. So ALA it is converted into porphobilinogen with the help of the enzyme called as the ALA dehydratase, and this porphobilinogen it is further converted into hydroxymethylbilane with the help of the enzyme porphobilinogen deaminase enzyme. So whenever there is deficiency of the ALA dehydratase enzyme, it will cause ALA dehydratase deficient porphyria. Also, due to the absence of this enzyme, there is elevation of these ALA levels. Okay. Now coming on with the acute intermittent porphyria. So whenever there is deficiency of the porphobilinogen deaminase enzyme, porphobilinogen and the ALA they get accumulated in the body, that is called as the acute intermittent porphyria. Also in both these cases they are neuropsychiatric manifestations because there is no porphyrin present, so there won't be any photosensitivity, so they will produce only the neuropsychiatric manifestations. Coming on with the heme structure, so every heme structure it contains 4 pyrrole rings along with Fe+2 in the center. So this green color it determines the pyrrole rings, and these pyrrole rings if they are connected with the help of methylene bridges, it is called as the porphyrinogen, and the same pyrrole rings if they are connected with the help of double bonds, it is called as the porphyrin. Yeah. So this is the porphyrinogen structure, and there are 8 substitutions over here. Depending upon the substitution, the compound is varied. For example, if acetyl and propionyl are substituted consecutively, so this structure it is called as the uroporphinogen. But in the last porphyrin ring, these are vice versa. So this structure it is called as the uroporphyrinogen 3. So So I'll just repeat it again. So there are 4 pyrrole rings, and in each substitution there is presence of acetyl and propionyl group. So if they are consecutively arranged in those substitution, it is called as a uroporphyrinogen 1, and in the last ring if they are present vice versa, it is called as a uroporphyrinogen 3. In the same place, instead of acetyl, if there is presence of methyl group and presence of methyl group and the propionyl group, it is called as the coproporphyrinogen. And same time in the last ring, if there is vice versa of the methyl and the propionyl group, then it is called as the coproporphyrinogen 3. And at the same time, when instead of methyl propionyl, if there is presence of methyl vinyl, it is called as the protoporphyrinogen. But these methyl vinyl groups, they are present only in the first and the second pyrrole rings. Okay. Now let me tell you how to convert the UPG and CPG and other heme intermediates. First, this is the uroporphyrinogen structure and this is the coproporphyrinogen structure. So the only difference is that in the place of the acetyl group, here there is a methyl group. So the acetyl group, it is converted into methyl group with the help of decarboxylation. So the enzyme required here is UPG decarboxylase. So the enzyme which is used to convert UPG into CPG is nothing but UPG decarboxylase. At the same time, as I already told you, propionyl, it is a saturated acid and vinyl, it is an unsaturated acid. So to convert this propionyl into vinyl, we have to remove an hydrogen, which is done by the enzyme oxidase enzyme. So to convert this, that is to convert CPG into protoporphyrinogen, we are supposed to use the enzyme called as the CPG oxidase. Now coming on with the protoporphyrinogen. This protoporphyrinogen, it is converted into protoporphyrin with the help of the PPG oxidase. So the difference between protoporphyrin and the heme structure is that in protoporphyrin there is no presence of the iron group, and in heme there is presence of iron. So to convert protoporphyrin into heme, we are using an enzyme called as the ferrochelatase, because we are going to insert a iron into a ring. So we are using the ferrochelatase enzyme. Yeah. So now coming on with the heme synthesis. This heme synthesis, it is occurring partly in the cytoplasm and partly in the mitochondria. So the ferrochelatase enzyme, this is a very important one mark, that is ferrochelatase enzyme, it is a mitochondrial enzyme, that is it is present only in the mitochondria, and also the coenzyme for all the decarboxylase, it is pyridoxal phosphate. So yeah, now coming on with the heme synthesis. So inside the mitochondria, glycine it is combining with the succinyl CoA in the presence of ALA synthase in the presence of pyridoxal phosphate to give delta ALA. This ALA, it is coming out of the mitochondria into the cytoplasm, and now it is combining with the enzyme called as the delta ALA dehydratase, and with the help of this dehydratase, we are converting delta ALA into porphobilinogen. This porphobilinogen, as I already told you, it is undergoing deamination where ammonia it is leaving, so it is converted into hydroxymethylbilane. Now this hydroxymethylbilane, with the help of the enzyme called as the UPG3 synthase, because you are synthesizing UPG3 here, so automatically the enzyme will be synthase. Remember like that. So hydroxymethylbilane, it is converted into uroporphyrinogen 3 with the help of the UPG3 synthase enzyme. And this UPG3 enzyme, with the help of the decarboxylase enzyme, it is converted into coproporphyrinogen 3. And this CPG3, it again enters into the mitochondria, where it is acted upon by CPG oxidase, and it is converted into protoporphyrinogen. And this protoporphyrinogen, it is again undergoing oxidation to get converted into protoporphyrin, and this protoporphyrin, it is converted into heme by inserting the iron with the help of the ferrochelatase enzyme. So this is the heme synthesis step, which is very essential, and it carries 15 marks, as you all know. Yeah. So the lead, it inhibits 3 enzymes of the heme synthesis. The first one is ALA dehydratase enzyme, second one is coproporphyrinogen oxidase, and the third one is ferrochelatase enzyme. So you can now coming on with the regulation of the heme synthesis. So there are various regulations. So the first one, the rate limiting step of the heme synthesis is nothing but ELA synthesis. So let me tell you what is rate limiting step. So rate limiting step is nothing but if the enzyme is absent, the total whole process is completely stopped. So an enzyme which is absolutely a requirement for the whole metabolism, which cannot be replaced by any other enzyme, it is called as the rate limiting enzyme. So only in the presence of the ALA synthase enzyme we will be able to convert glycine into heme. So yeah, so the most important or the rate limiting step of the heme synthesis is nothing but the ALA synthase. So this ALA synthase, it is of two types, ALA synthase 1 and the ALA synthase 2. This ALA synthase 1, it is present in the liver, and this ALA synthase 2, it is present in the RBC precursors. Yeah, and this ALA synthase 1, it is related to the heme enzyme synthesis like the cytochrome P450. That is, this is responsible for the synthesis of the heme, and here this ALA synthase 2, it is responsible for the synthesis of the hemoglobin. And this ALA synthase 1, it is chiefly regulated by heme because it is feedbackly inhibited by the heme. Here it is regulated by the iron availability and the rate of the erythropoiesis. The second regulation is that when enzyme inducers are taken, it utilizes the cytochrome P450 at a faster rate. So heme should be synthesized at a faster rate. So whenever you are taking an tablet which is like an enzyme inducer, so it will trigger cytochrome P450 at a faster rate, which will tell you that heme should be synthesized at a faster rate. So what will happen is that heme automatically get reduced, and ALA synthase 1, it is increased, and all the heme intermediates accumulates, which is a reason for the porphyria. Now coming on with the starvation which can precipitate the porphyria, and the last one is that the attack of porphyria can be treated with the help of hematin administration or the dextrose. Now ALA synthase 2, this ALA synthase 2, it can be regulated when, so as I already told you, this ALA synthase. Now coming on with the regulation of the ALA synthase 2, as I already told you that ALA synthase 2, it is regulated with the help of iron availability and also the rate of erythropoiesis. So whenever there is increased rate of the erythropoiesis, there will automatically be increased transcription of the ALA synthase 2. And whenever there is availability of iron, there is more, there will be increased translation of the ALA synthase to RNase, and this PPG deaminase, it is feedbackly inhibited by CPG and the protoporphyrinogen. Yeah, now coming on with the porphyria, that is the main topic. So there are various porphyria, so we will discuss here. Yes, so ALA synthase defective. So here the heme, it is not formed, as I already told you that in neuropsychiatric manifestations, because of the absence of the ALA dehydratase enzyme and the porphobilinogen deaminase enzyme, there is no porphyrin present, or there is no porphyrin produced. So there won't be any photosensitivity, and also heme is not formed as there is no presence of heme, it will present with anemia. So this is called as the X-linked sideroblastic anemia. Okay. Now apart from the ALA synthase defect, the defect in all other enzymes will be only partially defect, because in all other defect there will be production of the iron some or the other ways. So if there is no heme synthesis, there will be some other methods for the production of the heme. So that is the reason that there will be only partial defect over here. Usually here whenever there is ALA synthase defect, whenever there is a defect other than the ALA dehydratase defect, there will be decreased in the rate of the heme synthesis, and there will be decreased in the availability of the heme in the feedback mechanism. It will stimulate the delta ALA synthase. So automatically there will be production of the heme. Now as I already told you, there are two types, neuropsychiatric manifestations and the photosensitivity, and some porphyria, it can exhibit both neuropsychiatric and as well as the photosensitivity manifestations. So as I already told you that there are two types, that is neuropsychiatric manifestation and also the photosensitivity, and in some cases there may be both of them. So let's first see about the neuropsychiatric manifestation. So the first enzyme of the heme synthesis is ALA dehydratase enzyme. So when there is ALA dehydratase defect, so ALA, it will start accumulate, which is toxic to the neurons, and also as I already told you that there is no porphyrin formed. The next enzyme of the heme synthesis is nothing but the porphobilinogen. It is converted into hydroxymethylbilane with the help of the enzyme PPG deaminase. So the defect of the PPG deaminase will accumulate the ALA and the PPG, which will be causing the acute intermittent porphyria. Now coming on with the photosensitivity porphyrias. So yes, first one, it will be UPG3 synthase defect. Whenever there is UPG3 synthase defect, it will cause congenital erythropoietic porphyria, and this is the most severe of all types of the porphyria, and it will lead to the accumulation of the UPG, and also it will present with photosensitivity, as I already told you. Next, coming on with the UPG decarboxylase defect. Now coming on with the UPG decarboxylase defect, it is also called as the Porphyria cutanea tarda, and it is the most commonest type of the porphyria, and where UPG3 it starts accumulating over here. The last type of the photosensitivity it is that ferrochelatase defect. As I already told you that it is a mitochondrial enzyme, ferrochelatase. Here the protoporphyrin, it is starting to accumulate, which is causing the erythropoietic protoporphyrin. Now let's see what are the porphyria which will cause both neuropsychiatric manifestation as well as the photosensitivity. The first one, it is CpG oxidase defect, which is also called as the hereditary coproporphyria. Here CpG3 it starts to accumulate, which will cause photosensitivity, and also CpG3 it feedbackly inhibits the PPG deaminase enzyme. So additionally porphobilinogen also accumulates, causing the neuropsychiatric manifestation, right? Yeah. In both of these enzyme alone, in CpG oxidase and also in the PPG oxidase, both neuropsychiatric and the photosensitivity manifestations, both of them they are seen. And here again protoporphyrinogen oxidase, it is defective, it will cause you variegate porphyria. Here PPG3 accumulates, causing the photosensitivity. Additionally also inhibits the PPG deaminase, which accumulates porphobilinogen, causing the neuropsychiatric manifestations. Yeah. Next, most porphyrias, they are mostly autosomal dominant except 3 exceptions. The first one, it will be ALA dehydratase deficient porphyria. The second one, it is congenital erythropoietic porphyria, and the last one, it is erythropoietic protoporphyria. All of these three, they are autosomal recessive, whereas the other porphyrias, they are mostly autosomal dominant. So alright guys, that's all about heme synthesis and porphyria. So if you like this video, please do like, share and subscribe to my YouTube channel, and also if you want more such videos, please do mention in the comment section, and I like to do that also. So see you all soon. Bye.